Hi, welcome to the Signal Pad. In this episode, we're going to try another repair, and if this looks strange, that's because I lost the introduction clip already. I erased it by mistake, so I had already taken this apart. This is a Fluke 744 Documenting Process Calibrator. These things can be still quite expensive. They provide reference voltage resistance, current temperature reference, and so on. It even has a HART interface for calibrating some standard units. So these are pretty handy around the lab if you want to check something to see if it's calibrated properly, and this thing has a whole bunch of other capabilities. Unfortunately, this wasn't turning on at all, and it came in a terrible shape. It was missing the battery, it's missing the battery cover, unfortunately, so even if you fix that, that's still going to be missing, and I couldn't do anything with it, so I decided to just open it and see what's going on the inside. So we really haven't missed much. We can jump right back into it and see what's going on. And when you open the unit, it's kind of made of 3 layers of various PCBs that are stacked to each other. There's actually not a lot of room inside that box. It's quite nice to see. So as you can see, there's the board here. This board is the input interface board. The power supply is over here. The HART interface, serial interface are all over here. Little daughter board translates that directly onto this main board with a ribbon cable. There's a transformer there. It could be just for isolation or maybe magnetically coupling something in. I haven't looked at it very closely yet. This board is clearly responsible for most of the power supply activities, and I think in fact somewhere around here, there you go, it says that this is the power supply board. Voltage regulators, DC-DC converters, a bunch of MOSFET switches, which is probably for soft power on, and a few other op-amps and comparators occupy this board. There do appears to be a relay and some precision resistors here as well, which is interesting. Battery terminal, as you can see. This instrument doesn't actually have any battery charging capability. The battery has to come out, as I just mentioned. So this is really just a switch over. And other than that, I don't think there is anything in there. On the other side of this board, there is really not much there neither. From that, several connectors go into this board. This is obviously the brain of the whole thing. We have a Motorola 68000 processor here. This looks like the interface to the display. This is our display right over here. There is a battery in here, most likely for some backup of settings and so on. I see a few other components. There's some SRAM memory or flash memory around, which is probably the firmware being loaded. There's a Fluke branded IC here, and I think this is responsible for all the functionality, like the multimeter capability and a lot of analog functions. This is basically the magic of this instrument. On this, I don't even know if this chip works. We can't turn it on anyway. Some buzzer and a few other things around, nothing really unusual. I think there's a DAC over here, probably responsible for some of the analog functions, not the analog functions over here, but probably controlling some of the other things that are on the board. You can see nice terminal for the thermocouple. This is our keypad, and the buttons are on the other side, and it has a membrane that has to touch, of course, these guys over here. Right? It's quite dirty still, has to be clean. This also had a nice little shield board that sits right over here. You can see this is covered with metal at the very top, and you can screw this over there and it grounds the whole thing. So that's how they shield the power supply from the main board. A lot of work has gone into putting this thing together. This is not, some afterthought, of course. And let me see, there was a few other things I wanted to mention over here. Let me look on the other side of this. As I mentioned, there's not much over here. This is another shielding that goes into the body of this whole thing, a bunch of other components on this side. And if I were to flip this, there's a few other components on that side as well, but again, nothing really unusual. So it doesn't turn on, which means that we're gonna plug it in and find out what's going on, and we're gonna find out what part of this entire circuit actually is alive when we plug it to the power supply, because this has to have some kind of a standby voltage because it has a soft power arm, and therefore some activity must be present over here to turn the unit on. So we're going to look for that. I'm also going to look for to see if there's any way to get the schematic. There's absolutely no information that I could find, but I did find the schematic of a much older unit, and I have a feeling they have reused quite a bit of this in that too. So maybe we can get some hints from that schematic and bring it over here. All right, so let's take a look at this schematic here. Now, this is not the right schematic. This is the schematic of the Fluke Process Calibrator 701 and 702. This is 744. This is a very, very old model, but I do think that there are a lot of similarities and there are a lot of reuse. And this is not unusual because in a product evolution, a lot of the circuitry you've done, especially the power management, things that don't really change are going to stay the same, which is nice. So let's take a look in over here. So we have an AC adapter input over here. It's funny they call it an AC adapter here, not a battery eliminator. And we have a circuitry over here, which has something to do with the battery. Let's forget that. And here we go. There's a MOSFET here. And this MOSFET is controlled with the power on line over here. And it's got this feedback back around this other MOSFET Q3. So it's a latching power on circuit. So once it's on, then this MOSFET basically stays on. You don't have to keep holding the button down in order for the unit to stay on. These soft power on circuitry are extremely common, and they have to be done fairly carefully because soft power on burns power constantly when the device is not on and therefore drains the battery. So an ultra low power soft power on circuitry is very important in these devices, especially these handheld multimeter kind of things. We have some low battery indicator that's probably not that important in this case, and you can see the output of this goes into two regulators. And these look like two 5-volt regulators, so these are probably those two big regulators that we saw on the power supply board. Interesting to see that on this board they have the LED brightness for the backlight as well as the LCD contrast, also driven from two analog voltages. LCD contrast and LED bright are coming from inside somewhere, probably driven by a DAC somewhere. There's some op-amp circuitry over here to do that. This transistor Q12 is a driver for the backlight LED. Nothing unusual really. Looks like, I'm not sure what they're doing here. There's some kind of a power supply voltage generator of some kind. Oh, it's a virtual ground generator. Okay, that's the VSS generator. Okay. Anyway, nothing really unusual. Let's keep going. This is interesting. So this is a transformer here, and that's the transformer we saw, the one on the power supply board, and this is clearly a DC-DC power converter. They've built the simplest power converter they could. There's a they're using an HC74 series logic in feedback to create a 200 kilohertz oscillator, and then divide that by 2 to a 100 kilohertz 50% duty cycle oscillator, and that is driving two MOS transistors, Q10 and Q11. And these two drive a push-pull configuration into the primary of this transformer. It has multiple secondaries, and they all going through various rectifiers. You can see different rectifiers to generate different kinds of power supplies, and these must be probably further rectified. Some more power supply section over here. These are probably now beginning to look like circuitry for the actual power supply generator for the calibrator itself, not for power management. Let's keep going. These are all not that useful to us. What section is this? This is still okay. They're now beginning to be there in the main board. There you go. The beeper is there, so that makes sense. There's some kind of clock divider and so on. Anyway, I'm not going to worry about this. Lots of power supply decoupling. There's some explanation over here. I'm just kind of browsing it to familiarize myself. There it is. Here's the MC microcontroller, the Motorola MC 68000 series. And you can see all of its connections. I already see some differences, unfortunately. This one has a lower RAM and an upper RAM IC and a flash IC. So you can see these are all on various data buses. The RAM is obviously for storing and running the program in memory, and the flash is for grabbing the instruction set. This instrument that I have right now has more of these ICs. So it's obviously an upgraded version with more firmware, more storage. So that's already different. This thing seems to have a crystal up here and a crystal down here, which is also interesting. Two different crystals running this. There is a JTAG port for programming this initially, and I do think I see the JTAG port on this board. Obviously, there's not much we can do with it because we don't have the firmware. Here's the keyboard. That's also interesting to look at. Now, the keyboard uses a multiplex function in order to detect which key is pressed. Very classic architecture. But you can run this while the unit is in standby. And normally if you do that, you're going to burn a lot of power by the switching and the activity there. So you want to keep this into absolutely lowest power condition. And therefore, usually, there you go, there is one. There is a dedicated button that's wired a little bit differently. That's the power button. So when you press that, you turn the unit on, and then this entire section turns on. In fact, you can see we have a keyboard enable function that runs the power supply, looks like, of all the inverters or the drivers here. At least that's what I think is going on, and all of that is then begins to be active, and you can then interact with the keyboard. And there is a section power off. You can also power it off, and that is a unusual circuit. There you go. So something must be able to turn off that MOSFET that we saw on the other board, and that has to be done. Usually it's not done by the processor, but although it can be, where the processor basically turns itself off in the middle of some instruction if it wants to, but this seems to be overwritten by something else. Now this bipolar over here is AC coupled. This is interesting. That means that there must be some AC signal present on this, and this looks like an interrupt request RTC. Oh, there's a real-time clock here somewhere. Here it is. There you go. There's a real-time clock here, and that real-time clock is probably used for keeping time and everything, as well as creating interrupts to bring certain functions into the foreground of the processor as it is running. And it looks like that signal over here actually comes from this. That's interesting. So this has something to do with the power off circuitry as well. It looks like unless there has to be some activity on the real-time clock in order for this to even be active because of the AC coupling. some unusual circuitry. Again, this could be totally different, but there are some similarities for sure. There's some other circuit here. This is a reset switch. Oh, that's not populated. This looks like an IC for detecting whether there is the battery function there. I'm not quite sure. I have to check that as well. And looking over here, there's the LCD display control. That's probably that Epson part that we saw on the board. So beginning to have some idea on the architecture of this. Continuing on, and now we're getting in deep into the analog functions. These are a lot of optocouplers. They're probably from various power supply section into opto-isolators between the power supply functions and the main processor board. In order to obviously be noise isolated. Lots and lots of analog functions over here. Let's not worry about that. None of these things matter right now, because if it doesn't turn on, it's not because of this. It has to do with something else. Oh, here is that crazy chip from Fluke. Look at that. There's tons of functions in there. This is a totally custom-made part by Fluke, surrounded by their own analog components as well. Continuing on, some more circuitry. Let's ignore that. And to the main board. Yeah, that's it. I think the rest is really nothing. Here's the keyboard, PCB. Okay, so now we have some ideas. I think I get at least an idea of what the power supply section is. So we can now connect it back to a power supply and play around with it. So I did some poking around this to find out whether this power supply is center positive or center negative, and it turns out that it is a center negative, and that's a good thing to know, because otherwise it's not good. Although it does have a diode protection, so if you reverse bias it, it doesn't matter, but of course nothing works. So right now I have it hooked up to my power supply here. It's connected to this Keithley power supply, and the reason I'm using this is because it is a fantastic power supply with a 6.5-digit multimeter built into it. So I can turn it on and we can see the current consumption of the device is settling down now. And look at how many digits. This is in milliamps, by the way. So we're burning 0.006 milliamp. And just to convince you that that's really the standby power of this instrument, not just some random reading, I can go ahead and disconnect the power supply from the unit. You can see that it goes down to almost zero. There's a little bit of an offset there, and the power supply hasn't warmed up fully yet, but I can hook it back up, and indeed it goes back. So you can see that this thing, it doesn't really burn so much power in standby mode as to be expected. So now we can go ahead and try and turn it on and see what happens. So very carefully, you can get this over here and put this exactly right on top and try to turn it on. I think it's like that, and we see nothing, absolutely nothing. But here's an interesting thing to show you. Here, let me show you this. Check this out. Look at this. So here's our power consumption. So I'm going to do exactly the same thing. I'm going to try and turn it on by pressing the power button. Look, when I press the power button, it burns a milliamp. Yeah, so it's trying to do something. And in fact, if I press it gently, look at that. That's interesting. Yeah, let's go over here and look at the graph. Yeah, look at that. So I'm going to try and gently press it, slowly, harder and harder. Look, I can create an analog function. So there is the resistance matters. So there's obviously some kind of a comparator that is trying to use, and it doesn't fully switch. And sometimes these buttons are actually dirty. Let me try a different button. The power button might be used. Let me use a different button somewhere else and press. And let's try that again. Oh, look at that. It turned on. Huh. Oh no, it didn't turn on, but it is burning a lot more power now. Very interesting. It's now burning 224 milliamp. That was an interesting find. So all I did was, in fact, use this button, which is exactly the same shape. It's the opposite side. So yeah, so this membrane has gone bad. That's interesting. So there you go. This is the one I pressed, but now I can't turn it off. Oh no, that's not good. Okay, so it doesn't turn off. So let's disable it and turn it back on. So it's off again. I'm going to try and turn it back on again using the same button. And let's see. Yeah, I can do that. Well, that's unusual. Well, I can't turn it off, so something is still wrong, but I did manage to turn it on. That's a new find. And I did notice something else that you might find interesting. So let me go ahead and turn it off again. And let me put this guy like so. Make sure I'm not shorting anything. And look. have your eye out on the LCD screen over there. I'm going to try and turn it on. If I can get this lined up. I can't do it. Did you see that? It blinked for a second. The backlight came on and then went back off. So that's interesting. Okay, so it does turn on, but then it doesn't do anything. That's actually a pretty bad sign, because it means that it powers on, but the processor is not doing anything, or this entire signal flow is not working. But the fact that the backlight doesn't stay on, and the fact that I can't turn it back off, really concerns me. So let's go ahead and use the Rodenstrauss RTO 2064 to do some measurements around the board. Now I'm not looking for anything in particular, I just want to see if various signals are present. So the board is powered on, there's nothing happening of course because it doesn't do anything yet. But we can go ahead and measure some critical things. For instance, we can measure the power supply on the processor to see if there is a power supply voltage there. And indeed you can see that we have a 5-volt power supply. So the power supply portion is most likely working as the digital stuff's all powered on. I've already checked that. We can check the oscillator, for instance. Where's the output of the oscillator? There it is. So we have an oscillator onto the processor. That's a good sign. We can check to see if there is any activity on the board in terms of digital activity into the memory portions. Let's check a couple of these digital bits. There you go. You can see there is indeed activity. So the processor is doing some stuff. It's just weird that despite all this activity on various places on the board, we still don't see anything on the screen. Now I've also checked the screen, and there are some bits that come and go into the screen. Here's another one. It looks like some kind of a strobe line, and still nothing shows up on the screen. And the backlight doesn't show up neither. Now the reason I don't suspect the screen is because I can't turn the device back off. And we discussed that in order for a device to be able to be turned off, it needs to have the processor and it needs to have that interrupt signal from that real-time clock module there. So maybe we should go back and evaluate the board a little bit more to see if that real-time clock has anything to do with the operation of this and whether that's critical or not. It's hard to know because we have no schematic and no information about the firmware. What I'm worried about is that the firmware is corrupted. In that case, there is really nothing that I can do to fix it. But nonetheless, let's go and take a look and see if we can learn anything from the real-time clock. So let's turn our attention to this real-time clock module here and take a closer look at it. So one of these pins is not used, but the interrupt pin comes out of over here, and this is the same pin that then makes all the way over here and it goes into this portion. So in fact, if you don't have an interrupt signal coming out of this, I don't think this power off portion even would work because it's AC coupled and only appears to react to a change in the signal at the input of this base of this PNP device. So let's go and dig out the datasheet of this part. I have it over here. There it is. So this component is interesting because it has a built-in crystal. So it's a full module that combines the crystal and IC and a whole bunch of other stuff in order to do the real-time clock functions. It still needs an external battery. It doesn't have a battery built into it. But we can go down here and see its pinouts. Some of these numbers, I mean, we can look at these, but it's not that important. Where is the pinout? Actually, here's the block diagram. This is interesting to see as well. So because it has its own crystal on the inside, you can see, and according to this block diagram, it seems that this divider will produce a 1 Hertz output. And this is a 32,768 kilohertz clock, very common. It's because it's a power of 2 in Hertz, and that makes division by a factor of 2 very easy to get to 1 Hertz. And it has a whole bunch of registers which you can program, and the device would then generate an interrupt function. That interrupt function would happen based on the configuration on a repeated pattern of timing. It's basically a complex timer. So I'm thinking that maybe in the absence of this activity, the software is waiting for an interrupt and it doesn't advance. This is obviously a bit far-fetched, but nonetheless I think it's worthwhile to taking a look at it. Where's the pinout? I think I did see the pinout somewhere. There it is, the pinout's over here. There we go. So we have all the pins here. We can take a look at it. If I go back to the schematic of the instrument or the old instrument, again, I don't know if it's wired the same way, but it looks similar. We should be able to look at some of these data pins, look at this 1 Hertz output, look at this interrupt output, and see if there is any activity on it. And here's the back of the board, and you can find the memory modules right over here. You can see it has twice as many memory as the schematic of the older version, the 701 shows. And here is our real-time clock chip. And we can check a few of these properties here. So let's make sure it has power supply. That's pin 24. There you go. Actually, what am I doing? You can't even see the screen. Here's the screen. So let's check the power supply. There you go. Indeed has power supply. There's some noise on it, but it's okay. So let's look at the output, the interrupt output. Here it is, pin number 3. Ah, look at that. It's stuck at high. So it has no activity at all on that interrupt. So no wonder we can't turn the device off, because if it's just constantly sitting high, I don't think you can trigger that PNP device to be able to turn the device off. Let's look at the 1 Hz output. This is the 1 Hz output, and no, doesn't look like there is anything there. We can look at one of the address bits, and this address bits is what the processor is writing onto it. There you go, see, there is activity. So the processor is indeed talking to it, but it doesn't seem like it's generating any interrupts. That's interesting. So it's a bit of an unusual behavior. Now this may have nothing to do with the problem, maybe it's not even being configured correctly, and therefore it's not generating any interrupt. But the fact that it's not generating any 1 Hz output is a little bit strange. So I'm going to go ahead and search on eBay, see if I can find the replacement IC. At least we can change it. Really, there's not much else we can do, but it's worthwhile trying it. And check it out, with the magic of television, now we have one directly from China. It took a while for it to arrive, and it was about $20, which is, quite expensive. But now we can go ahead and remove this and replace it with this one to see if there is any difference at all in the way the device operates. Alright, here's the part gone. It's interesting to see the glue pads that we're using underneath it in order to hold it so that it can be soldered on both sides. Then this is a fairly old board from '97, so yeah, the glue they use is quite harsh. So I went ahead and replaced it, and unfortunately the result is exactly the same. I do want to x-ray this module to see what it looks like on the inside. I think that would be still interesting. Let's go and try that. And here's the x-ray of the module. It's kind of neat to see inside the package. Here's the classic 32 kilohertz crystal that we see all over the place. It's bonded to 2 of the traces inside the package itself, and of course then comes back into the die, and then all the connections around the die are present. You can see these 2 pieces of metal come to the edge of the package, and I did manage to measure them even through the package. Just a tiny bit of contact left, and indeed there is a 32 kilohertz signal there, so therefore that means that this is just being misconfigured, and that's the reason it's not working. Yeah, so I think we're going to have to give up on this for now. I think this is a firmware issue. The firmware is corrupted and the processor is just, stuck in something and it cannot continue. I cannot think of anything else that could be wrong with it. I've checked, 100 different things on this board. They all lead to the same result. I'm going to post this video anyway because I'm hoping that maybe somebody knows how to interface with this JTAG lock interface and flash this and reprogram it. That could potentially save it. So I hope that you enjoyed this nonetheless, and if you know any information about how to get this firmware, or if you know anything else about what could be wrong with this unit, please let me know. I'll see you next time.